Sir, can we start?
Yeah, I'm ready. Anytime you tell me.
Please, sir. Just now, I give the brief introduction about you, and then we'll start the session, sir.
Sure.
Yeah. Yeah. Very good morning to all of you. I think today is the last session of this virtual online workshop on fundamental aspects of quantum mechanics. Today's resource person. It is an immense pleasure to introduce our today's resource person, Dr. Vivi Sridhar. He is a professor of Chennai Mathematical Institute, Chennai. I have to tell about the brief CV about the professor. He did his master's in physics, IIT Madras, and did his research PhD in the Saha Institute of Nuclear Physics, Kolkata. His previous positions are faculty, Department of Physics, IIT Kanpur, and his uh, doctoral positions in Dublin Institute of Advanced Studies, Ireland, and Uppsala University, Sweden. So his long-term visiting positions are Bose National Center for Basic Sciences, Kolkata, Rahman Institute, Rahman Research Institute, Bangalore, Rochester University, and Cincinnati University, US, and Tsukuba in Japan. So I think such an eminent professor we have today. He is going to give a lecture on an invitation to path integrals. With this brief introduction, I hand it over to Professor. Over to you, sir.
Okay, thank you very much for your kind words.
Thank you,
I
sir.
hope I'm audible to everybody.
Participants, I think, is it clear, sir? It is clear.
Okay, good. So let me, without further ado, let me just start my talk. Um, I'll just begin by sharing my screen. Um,
Yes.
yeah, I hope everybody can see this. I'll try to make it better. Okay, I think, is it clear to everybody now? Can everybody see this?
Screen sharing, the title is not visible now, Professor.
Can everybody see the screen? Can you please, somebody can confirm?
No, sir.
You cannot?
Yeah, it is not visible now.
Okay, let me just check. Okay, no, it's not visible.
1 second. Ami, sir? Dr. Ami? Amiruddin, sir?
Okay, let me just.
Here the screen sharing is activated, Professor.
Okay, I'm just trying to see why it's not coming. It just now came, right?
Yes, sir. Yes, sir. I saw there the initial.
Okay. Is it okay now or not?
No, sir. Not yet visible. Sir, can you sign out and sign in again?
Yeah, I'm just trying to do. You can't even see my face?
No, sir. No, Professor. I think you are muted the video. Yeah, now it is. We are seeing your face.
Okay, now let me try.
Yes, sir.
Now can you see?
No, sir. It shows here you are started the screen sharing, but it is not. I think you can open and click that screen, and then you can open that file, sir. I think it may be.
Your screening, it says stop share or not.
Yes, sir. Stop share and start again, sir. I think try again.
Okay. No?
No, sir.
How come it just sometime back it worked, right? So
Yes, sir. Yes, sir. Initially, I saw there that title of the today's talk.
so maybe I should just log out and try again.
Yeah, log out and log in, sir. I think it's. Yes, Professor, you joined. Professor, can you unmute your video? Yeah.
Yeah.
Yes, sir. We are seeing now your face.
Okay, let me try to. I think you should enable sharing.
Professor, it is already enabled. One second, I'll do it again. Yeah, now it is enabled again. Yes, sir.
You can see it now?
Yeah, the double slit experiment. Yeah.
Thank you.
Okay, is it okay now?
Yes, sir. It is visible now.
Okay, so so let me begin. I apologize for that slight delay. I'm not very technical.
It usually happens.
Yeah. So welcome everybody. I believe all of you have had some exposure to quantum mechanics, and today, and you have been listening to some advanced topics over the last 4 or 5 days. So today is the last day, and maybe we should finish off on a slightly fun note. So I chose a topic which is actually fairly advanced, but it's rooted in something very, very basic and fundamental. And that's why I titled it An Invitation to Path Integrals. Towards the end, it may become slightly technical, but I hope I will lead you through the path in small steps so that you can appreciate actually the logic of the entire thing. So I apologize if I don't cover a lot of ground, but I will certainly hope to whet your appetite in this field by telling you why it is important and the way people thought about constructing path integrals and so on and so forth. So if you have any questions, please don't hesitate to stop me. I may not be visible on the screen, but I will certainly pause and try to answer. And if not, please don't hesitate to send me email or something later on also if you would like to get some clarifications. So with these few words, let me begin the talk as such. Now, interference phenomena are well known in wave physics. So whether it is electromagnetic waves or acoustic waves or any kind of water waves, etc., interference, it is the nature of waves to interfere with each other. So this is something which we are very familiar with. Now, the standard experiment that is cited in this context is the famous Young's double slit experiment. So let me try to see what this Young's double slit experiment. Let's briefly recapitulate what it is. So what you have is basically a picture like this. Let me try to show you a picture. Yeah. So you have a screen on which there are two slits, A1 and A2. So to the extreme extreme left of it, although you cannot see it, roughly where the two dashed lines are converging, that's where there's a source of light. And light comes from that source of light and it falls on the screen. The screen obviously blocks the light, but then there are two slits, A1 and A2, through which the light can penetrate.
Professor, sorry for the interruptions. I think the image is not moving. The next slide, are you showing the pictures for now?
Okay, I understand. So I was sharing. I have to share this separately. Okay, one second. Yeah, I have to go back to my screen sharing thing and.
Sorry for the interruptions.
No, not at all. It's good. Oh, this is going to be slightly messy. Okay. So how do I share this one? I have to share this one now. Right. Can you see it now? Can you see the picture now?
It is not it. We are seeing here you started the screen sharing. That's alone. The message is there in that screen. Started the screen sharing.
Maybe the other one, I should turn it off or what?
You start the screen and then you click that screen and go to that slide, sir.
Now, can you see?
No, sir. I think participants, are you seeing anyone?
No, sir.
No. Okay.
No, sir.
Let me see what can be done. Okay. Screen share.
Can you unmute your video also and then try, sir?
Yeah, 1 second.
Yeah, we are seeing you now.
Yeah. Let me try to get that picture.
Yeah.
Can you see the picture now?
No, sir.
Oh. I have shared it here.
Okay. So maybe before sharing, you can open that file.
Can I just say I have about a half a dozen pictures like this. Now it's
Okay.
going to take forever. Is it possible for me to just mail these figures to you and you can display
Yes,
them
sir. Yes,
whenever?
sir. Okay, sir.
That will be much simpler, right?
Yes, sir. Yes, sir. You can.
Yeah. Okay. So just give me I'm
Yes,
sorry
yes.
it is taking. I'll just send
Yes, sir. Yes,
it.
sir. Dear participants, please wait. Once it is shared, we will share you. Please wait.
Just Yeah, I sent the mail.
Yes, Professor, just now I got it.
Yeah, so that YDS one file is there. No, please display that one.
1 second. Amit sir?
YDS.
Yeah. 1 second.
YDS.pdf.
Sir, is it audible? Are we visible now?
Sorry?
Is it visible now? I just shared the screen.
No, sir. Professor, can you stop the screen sharing?
I have to stop. Okay.
Amit sir, you can share
Yeah.
it now.
I have already
Yes,
shared.
sir. Yes, sir. Yeah.
Yeah. So you see this? Can everybody see this?
Yeah, audience, participants, is it visible to you?
Professor Sridhar, good morning. Kapoor here. We can see it.
Yeah. Okay. Very good. So so what you have here is. Can I continue?
Yes, Professor. Yes, Professor.
Yeah. So what you have here is unseen here to the left, on the extreme left. There's a source of light from which there's a beam which is emanating, and it is falling on the screen. And the screen obviously is going to block all the light except at these two holes, A1 and A2. These are the slits through which the light passes. And then here on the extreme right, you have another screen where you're going to detect. So the O is the observer, and the unseen S is the source, and A1 and A2 are the two slits. So this is the setup for the Young's double slit experiment. Now this might not look like a a great fantastic thing. It looks very simple, but what this contains some extraordinary physics comes out of this rather simple setup. So what happens? Can anybody guess what is going to happen? Well, what really happened? Sorry?
Interference.
Interference. So what really happens is the following. So the light from the primary source S gets split up into two secondary sources now. One source is at A1, there's another source at A2. So there are two sources of light now, and these two sources of light are going to interfere on the screen. So when the amplitudes, when the two waves which come from A1 and A2, they have the same amplitude, the amplitudes will add, and you will find a luminous spot on the screen. And when they are out of phase by pi, then the amplitudes are actually going to cancel each other, and you will get a dark fringe. So what you get on this screen on the extreme right is a series of dark and bright fringes as you go from the, let us say, the center of the screen. As you go upwards, you will find a series of fringes. So this is the Young's double slit experiment. So so that is fine. So one appreciates this very easily. Now, right. So one might wonder why this happens, and the usual explanation that is given to us is that this happens because light travels in waves. This is an easy explanation for this comes from wave optics. Okay, so but that the fact that light travels in waves was well known. Dating back to Huygens and such people, and this is precisely the Huygens principle that we are using here, that this source of light actually splits up into two secondary sources of light which interfere and so on and so forth. So this wave optics was father of wave optics. One can think of Huygens who did this. But then with the advent of quantum mechanics, we know that light is actually made up of small packets of energy which we call photons. So how does one reconcile this aspect of the wave nature of light with the particulate nature of light? So this is a question that naturally arises, and it is a deep conceptual question one needs to understand. But actually, before one tries to even attempt this, okay, let's try to make one thing very clear. So this is actually not just a feature of light. If, for example, you replace the source of light here by, let's say, an electron gun which is going to shoot electrons, what are you going to expect? Now, actually, it turns out interference experiments with electrons are somewhat difficult because electrons are very, very small particles. But let us say we do it with neon atoms, let us say, or we do it with hydrogen molecules, or helium atoms, or you name it. Okay, so take something which is fairly slightly larger than an electron, and then try to do this experiment. Now this is not simple speculation. These experiments are actually carried out. So in Japan, for example, there's a place where they have constructed a kind of what are called optical molasses. These are basically stationary laser waves in which you can hold neon atoms, okay, a bunch of neon atoms. Now these neon atoms, now you suddenly release them. So there's another picture for this. Can you please show that, Dr. Vijay Raghavan? There's a something called neon. Neon. Neon.pdf.
Neon.
Yeah.
Yeah, so you have these trapped atoms which are on top of this plate, and say these atoms are released, and they're obviously going to fall freely. Now there's you keep an obstruction. There's a big plate with small openings in it. These are the slits. These slits are, let's say, of the order of a few micrometers or nanometers or something like that, and then these atoms are supposed to fall through them. So there's a plate here. So what's going to happen? So people have actually performed this experiment, and on the right hand side you see these dark and bright fringes. So it looks like this is a feature not just of light but also of particulate matter like atoms. And in fact, people have improvised this. They have gone to larger and larger atoms, even up to what are called fullerenes. These are this Buckminster fullerenes. These are actually carbon-60 atoms, which look like a kind of a football of carbon atoms. Even with that, people have tried, and then people know for sure that there is this interference that takes place. So now we meet a kind of funny situation that whether we have light or electrons and or particulate matter, all of them show this interference pattern when they go through the Young's double slit experiment. They are subject to this Young's double slit experiment. So how does one explain this? So let me try to get my but I think once again it's a sharing thing. I have to share it now.
Okay, sir. Thomas, sir, you can
you
close it now.
Yes,
you can close your Can you see my presentation now?
Started the screen sharing only comes. I think you open that file and click and share it, sir.
Can you see it now?
No, sir.
Professor Sridhar, you stop sharing, open the file, and then click on the file.
Sorry?
You stop sharing, sir. First, you can stop sharing.
Stop sharing.
Open the file first. Open the file, sir.
Yeah, I opened the file.
Yeah, now you can share and click that file. It will open. Share it and open that file. Share it and click that file. It will be seen, sir, I think.
Yeah. I did that.
Did you click that file?
Yeah, I did.
No, it's not.
But it is not there, sir. It is not coming.
Okay, so I think I have no option except to send this file also to you. You should be, I think you seem to be able to share screen easily, right?
Yes, sir. Yes, sir.
So shall I send this file also to you?
Yes, sir. Yes, sir.
Yeah. Yeah, I sent it. Can you maybe just display it? It will be much simpler that way. There's some problem with my.
Professor, have you shared? Yeah, one second.
Yeah.
1 second. This Crescent PDF, Professor?
Crescent, yeah.
Yeah, you open that file.
Yeah.
1 second, so I'll download. Amish, sir, have you got it?
Yes. Let me check. Yes.
Open that.
Yes. Fine.
Yes, it is visible now.
Yeah, great. So, yeah, go to the next slide, please. You just need to press. Yeah, one more you press.
Amir, you can expand.
Yeah. Yeah, okay, stop here, please. Yeah. So, as I said, there are these two slits which act like secondary sources, and the waves are going to interfere. The amplitude is twice when they are in the same phase, and then when they are out of phase, that is when the phase difference is pi, then the amplitude vanishes and you get a dark fringe. So this is well known, right? So let's go to the next slide, please. Right, so this is what I was mentioning. You have neon atoms which are trapped in these optical molasses, and they fall through this two-slit device. That picture was shown of neon atoms falling through these two slits, and then you get an interference pattern. So as I said, this is also true for example, neutrons, helium atoms, hydrogen molecules, fullerenes, etc. Now the point is, atoms. Can everybody hear me? Can I continue?
Yes, Professor, it is audible.
Yeah, very good. So see, what is well known, however, is that atoms are actually point particles. Now, what does one mean by a point particle? Well, it's of course a question of a football is a point particle if you compare it with the size of the Earth is a point particle if you compare it with the size of the Sun. So what is a point particle? Why is an atom a point particle? Well, the kind of physics that we do, the kind of length scales with which we work, the kind of length scales that are involved when we actually do some experiments in the laboratory, from that point of view, an atom can be thought of as a point particle. Second, this point, if it's a point particle, then one can meaningfully talk about detecting this particle, it existing at a certain point in space, etc., etc. Now, atoms, for all practical purposes, they're of the order of a few angstroms, let's say, and then you can actually detect them very precisely. So if you capture one atom, let's say in a detector, then you say this is the position of the atom. In this detector, I have an atom. So the position of the atom is well known. And they're extremely well behaved. Just because you have captured them, they're not going to rebel against you, they're not going to disintegrate, they're not going to do anything. So for all practical purposes, an atom is a point particle. On the other hand, think about waves. If you go to the Bay of Bengal and then you have waves splashing all around, what is the characteristic property of a wave? A wave is something which fills all of space. So if you take, for example, a wave on the surface of water in the Bay of Bengal, by definition, it is the whole set of points of all the deformations on the surface at each and every point on the surface. Unless you define all that, you have not defined a wave. So wave, by definition, is something which fills all of space, which is quite different from the notion of a point particle that we think of in terms of atoms. It is the same dichotomy that is prevalent when you talk about, when you think about light, and you think about light in the form of photons, or you think about light in the form of waves. So there is a dichotomy. So this is something that one needs to explain in the double slit experiment. So can we go to the next slide, please? Okay. Now one might say that the interference that one encountered in the case of light is easily understood because, as I said, light, unlike atoms and particulate matter, you can always think of light as waves, and waves are going to produce interference. But the point is, I can actually reduce the intensity of light coming from the original source, and I can reduce it so much, and I know that light is a bunch of photons, and the intensity of this light is actually proportional to the number of photons. So I can reduce the intensity of the light that comes from the source so much that at any given point of time, I'm going to produce a single photon. So in other words, what we observe in interference in light, if one takes the point of view that it is not adequate to say that this can be explained using the wave nature of light, because one has to reconcile this with the fact that light is made of point particles, which are photons. Then one might say that, okay, maybe it is true that light is made of photons, but then these photons, while they are passing from the source to the observer, they are interacting amongst themselves, and that is what produces the interference pattern. Suppose somebody makes that kind of a claim, it has to be immediately countered by saying that actually, if you reduce the intensity of light and you let only a single photon travel at any point of time, then you will find that nevertheless, you might get a very faint interference pattern, but an interference pattern is nevertheless detected. So what this means is the following. The interference pattern that you see is not because of interference from external sources or interference between photons. It is an interference pattern that is produced even with a single photon. So that is to say that the particle in some sense interferes with itself. Okay, so the one has to kind of pause and try to digest this fact. If I let a single photon travel from the source and it meets a two slit surface and passes through it, and then it's detected, finally you find that there is an interference pattern. So something bizarre seems to be happening. This particle seems to be interfering with itself. Okay, now one can, obviously this is a very confusing state of affairs. So one might try to say, no, this cannot be. Let me actually try to do an experiment more carefully. So there may be two slits and there is a single photon. So obviously the photon has to travel through one of these slits, A1 or A2. Okay, so let me find out through which slit it has traveled. And if that happens, then the other slit is not there at all. It's for all practical purposes, it's not there. Therefore, the photon cannot produce an interference pattern. So suppose this is what we say. So what you try to do is to measure through which slit this photon is traveling. And by the way, whatever I'm saying for photons is now identically true for neutrons or hydrogen atoms or fullerenes or whatever, particulate matter. So the idea is same. What we are now aiming at is trying to understand the conceptual underpinnings of this Young's double slit experiment and what it leads us to. Okay, so the question now we are asking is, what if I actually if I keep an observer or somebody detector at one of these slits, and then I try to find out if the photon or the neutron is passing through that slit. So it so happens that the moment I try to detect this, then the interference pattern disappears. Okay, this is an experiment that one can do. So let's there's another picture that I've given there. Can you please show that picture where it's called detector.pdf.
Detector.
1 second.
Yeah, so here you see this is this source, and there is this screen with two slits A1 and A2, and there is this observer. This is all original stuff that we had. Okay, but now somebody is trying to be clever, and they want to put two photomultiplier tubes, F1 and F2 here. Okay, now they want to detect if F1 gets triggered, then that means that photon, because it's a single photon, it has passed through the slit A1, and if F2 gets triggered, it passes through A2. Now let's quickly see, is it possible, because you're going to, a single photon is producing an interference pattern, is it possible that both F1 and F2 will be triggered at the same time? If that happens, something remarkable is implied. What is that? There's a single photon and both F1 and F2 are detecting it. That means this photon has actually split up into two parts. But that we know is nonsense, because a photon is an elementary particle. It does not split up into anything. There's no subdivision. In fact, it flies in the face of logic of quantum mechanics, because it's a photon is a fundamental unit of light. It's right. So it cannot split up into two things. So what happens if one does an experiment like this? It turns out that sometimes that actually F1 gets sometimes illuminated because it absorbs a photon, and F2 also sometimes gets illuminated. It does not mean that at the same time F1 and F2 are illuminated. What it means is the following. I have a bunch of photons coming from the source, one at a time. So that photon will either pass through slit A1 or A2. So if it is detected in F1, that means it has come through A1. If it is detected at F2, it has come through A2. And statistically speaking, F1 will detect a photon as many times as F2. So statistically, there will be an even distribution, more or less. Okay, but it is never the case that both of them will be triggered at the same time. So if this is the situation, what happens to the interference pattern? Well, as I told you, the moment you put a photomultiplier tube like this, it's going to absorb the photon. So there is no photon actually reaching the screen. So you have destroyed the interference pattern. So there is no interference pattern. So there is no problem at all, no confusion at all. So what this is telling us is the following. If we have the temerity, if we have the audacity to try to figure out through which slit this photon is passing, A1 or A2, we have destroyed the interference pattern. So this photon does not like interference. It is an interference experiment, but the photon does not like external interference. It likes to interfere with itself, but not with others. So if an outsider comes to try and peep into this slit A1 and A2 to try to see if the photon is coming through this slit or that slit, that's it. It becomes shy and there is no more interference pattern. Is that clear? Yes?
Yes, sir. Yes, sir.
Yeah. So let's go to the next slide. So let us, the problem here is that this photomultiplier tube is absorbing this photon. So can we do something smarter? Okay. So let's show another picture, and that's the mirrors.pdf. Can you please show that picture?
Yes, sir. Yes. Yes.
Yeah. So, experimentalists are smart people. So they want to somehow understand this mystery. So what they do now is the following. They put a mirror M1, a pair of mirrors, a system of mirrors, M1 and M2. Okay. So if the photon is coming through the slit A1, it gets reflected at the mirror M1. And then you put another mirror, which is the pair of that M1, which is the partner of that M1, which reflects it back so that the electron will, the photon will finally go and hit the screen on the right. So you are not, instead of putting a photomultiplier tube which will actually absorb this photon, you are ensuring that the photon somehow reaches the screen. And similarly, you have another setup with the slit A2. Now imagine this M1 and M2 are mirrors which are kind of fixed to some other external apparatus which will detect. If there's a small kick to that M2, there will be a recoil which can be detected. Similarly, if there's a small kick to M1, there will be a recoil which you can detect. So what's going to happen is there's a photon which comes, it hits M1, gets reflected and goes to the screen for detection for the observer, or it goes through M2. But every time if it passes through A1, the mirror M1 is going to receive a small kick, and that you can detect. So without disturbing the photon, you will be able to find out whether it has passed through slit A1 or slit A2. How is the idea? Nice, right? Now it turns out that, so if you try it once again, if you have the audacity to try to find out through which slit the photon is passing, A1 or A2, by doing this kind of a trick, you will find that you have actually destroyed the interference pattern. That is to say that the kick the M1 receives will actually disturb the optical path of this photon sufficiently for the interference pattern to be destroyed. So this is leading us nowhere. You can do any smart experiment, and the moral of the story is the same. If you try to find out through which slit the photon is passing, you end up destroying the interference pattern. If you let it be, if the only thing that you're interested in is the fact that there's a source of light which is producing a photon, and there's an observer sitting on the extreme right screen trying to detect this photon, that photon somehow it makes its way through these two slits and it reaches there, it can be detected. The source is known, the end point is known. What has happened in between, we do not know. If we try to find out, we destroy the interference pattern. This is the summary of this experiment. Okay, let's go to the next slide, please.
Yes, sir. Shall I open the PPT or?
Sorry? Yeah, so there's after that neon, there is one more thing, covered.pdf, covered.pdf. Covered.pdf. Yeah, so it is actually, so now let's, so this is something we found that is something very fundamental, whether you do it with light or whether you do it with atoms, the problem is the same. If you detect, then there's a problem, the interference pattern is destroyed. So let's do the following. Let's take this neon example that we had, and suppose we cover one of these slits. Now what's going to happen? You drop the atoms again from the top, there's a single slit. So what you find is actually a diffraction pattern associated with the single slit, and that is what is shown here. Now I can do something else. I can actually try to cover this slit and leave that other one open. Once again, there is no problem. There's a diffraction pattern. Now classically, you would think that if both the slits are open, I just superpose these two things. But that's not what is happening. If you open both the slits, then you get a series of dark and bright fringes. This is something very, very bizarre. You should think about it. It's if you think of these two slits as two doors in a house, right? So if you leave one door open, this is what you get, diffraction pattern. If you leave the other door open, you get another diffraction pattern. But if you leave both the doors open, then you get a series of dark and bright fringes. It's as if saying that in my house, there are two doors. Then if I leave one door open, people can easily walk into my house and see whatever is there. But if I leave both the doors open, then there are some regions in my house which become inaccessible to the person. Okay, it's very, very bizarre. But that is what is exactly happening. So how does one understand all this stuff? So let's go back to my, I think for now the pictures are over. So let's go to the text. That crescent.pdf, please.
Yes.
Yeah. So, okay. So this is, I have summarized this thing. So interference is observed even if you send one photon or atom at a time. And if you make any measurement, it disturbs the particle sufficiently. It perturbs the state of the particle sufficiently that you actually destroy the observed interference. And it is incorrect to say, it is actually almost sacrilege for us to find out through which slit the particle has passed. So we cannot say whether the particle has passed through the first slit or the second slit. There actually, if we are able to say through which slit it passes, once again interference is not observed. Therefore, there must exist a third option which somehow corresponds to a passage through both the slits, and the photon or the atom passes through both the slits without actually splitting up. Because if it split up, then we would have observed that. So this is the puzzling aspect of this double slit experiment. So can we go to the next slide, please? Okay. So be that as it may. So let's come back. So anyway, so the moral of the story is that these atoms or photons or whatever, it is not just enough to say that I can explain the Young's double slit experiment using wave mechanics or using wave theory of light or particulate theory of light. It's somehow these atoms and photons, they behave like particles in the sense they cannot be destroyed, they cannot be they're indivisible, they don't break up, they don't disintegrate. So they are actually particulate. They can actually be detected on a screen at various points. So they are actually like point particles. But on the other hand, unlike anything that you know from classical mechanics, for example, the ancient caveman, he used to do hunting. He used to shoot an arrow. It's going to go and hit a wild animal. Well, he knew exactly, at least intuitively, without knowing physics, that there is a trajectory that this arrow is going to take, and so that it is going to go and kill the animal. Okay. And today we have satellites landing on the Mars or Moon, etc. There's a perfect trajectory they take, and these trajectories are completely and very, very accurately, very successfully described by Newtonian mechanics. But all that success in physics now seems to go out of the window by the simple Young's double slit experiment, where it is almost sacrilege on our part to ask what is the trajectory of this photon, what is the trajectory of this atom, which slit did it go. Forget about the entire trajectory. We are not even able to say through which slit it has gone. All we know is that it started at some point, it ended at some point. But we are not able to say anything whatsoever about the trajectory it has taken in traversing from its source to the point of observation. So this is the quandary that we are facing. Okay, and as I said, so the only resolution for this is to appeal to the counterintuitive nature of quantum mechanics, and we say the particle, it does not actually make sense in quantum mechanics to talk about the particle per se, but we can talk about the state of the particle. And somehow the state of the particle is that the particle, if it passes through the slit A1, we say it is in one state, through the slit A2, it is in another state. But in quantum mechanics, the superposition principle allows the particle to be in a state which is a linear combination of these two states. So that is what is the reason, the underlying reason for interference. Okay, so the professor goes on and on about this Young's double slit experiment this way, and unfortunately it turns out that there is a smart student in the class. So the student asks the following. So basically, what is the reason why the interference is taking place? As I already told you in the beginning, that if the two slits act like essentially like secondary sources, and the amplitudes are the ones that we add. If it is light, we talk about adding the amplitude of the light waves, but in quantum mechanics, we have to actually talk about adding probability amplitudes. So associated with slit A1, there is a state, quantum mechanical state. That is to say, there's a wave function. That is to say, there is a probability amplitude for the particle to go through slit A1. Similarly, there's a probability amplitude for it to go through slit A2. And we add these two probability amplitudes, and we take the modular square of it to get the intensity. And in doing that, because these are complex wave functions, you actually get interference terms precisely because A plus B the whole square, like Modi said, is not simply A square plus B square. Plus A, that is A square plus B square plus 2AB. Like that, when you add two amplitudes and take the modular square of it, you're going to get some interference terms. And it is those interference terms which are responsible for this interference. Okay. So the professor explains this resolution of this problem in the class like this, and there's a smart student who says, okay, fine, all that is understandable, but what if there are 3 holes in the screen? Suppose I make an extra hole in the screen. That's the question the student is asking. Well, the professor says, well, it's very simple. It's simple enough. All you need to do is you add the amplitudes of all the 3 slits and then square the sum to get the intensity. You will, of course, get a complicated interference pattern. Does it make sense? I hope everybody is with me still, or? Hello?
Yes, Professor.
So is it clear? Am I audible?
Yes, sir. Yes, sir. It is clear, sir.
Am I going too fast?
Nothing.
No, sir.
No, sir.
May I continue?
Yes, Professor.
Yeah.
No doubt,
so
sir.
This is
you
what
continue.
Yeah, sure. So if there are 3 slits, he simply says you add the amplitudes of all the 3 slits and then you square them, square the sum in order to get the intensity on the screen where the observer is sitting. So fine. But the student is very persistent. He says, suppose I add another hole, 4 holes, 5 holes, n holes. So obviously the professor is losing patience. He says, well, it's the same thing. You keep adding the amplitudes for all the holes, and you take the modular square of the whole thing, and you will get the interference pattern. Okay. But the student is unrelenting. He says, okay, what if I add another screen with a certain arbitrary number of holes in it? So the professor is quickly losing patience. He says, listen, young fellow, I haven't got all day for this. But don't you see, the answer is very simple. The answer lies in the superposition principle. The actual computation may be complicated, but all you need to do is to add the amplitudes associated with each of the holes and then take the modular square. That will give you the interference pattern. Now, then the student says, now what if I put a screen and drill an infinite number of holes through it? Okay, I keep on punching holes in the screen, so there are more and more slits opening up. But then this, what happens if you make an infinite number of holes in a screen? It is the same as actually removing the screen, right? So you have a Young's double slit experiment, but it's no longer double slit. You started drilling holes in the screen. You made an infinite number of holes. So Young's infinite slit experiment. That means actually there is no screen. So what are you left with? You're just left with the source, and you are left with the point of observation. Will you get an interference pattern or not? Should you get an interference pattern or not? What will be the amplitude of the particle if I observe it? If the observer observes it on the screen, where he's sitting, it has come from the source. It has come through a screen which has an infinite number of holes, which is a fancy way of saying it has come through a screen which is non-existent. So basically, the particle has traveled from its initial points to its final point through vacuum, through free space, nothing in between, no obstruction. Does it make sense? This is what the student asks. Well, professor says, so what do we do? So here is a kind of a philosophical statement that is being made. A screen with an infinite number of holes is really a screen which is not there. So, like some English poet said, right? This heard melodies are sweet, unheard melodies are sweeter still. It's like that. It's like a melody that you have not heard. So if there's a screen, you think of a screen. So another way of looking at it, if you want to define something, then one way of defining that something is by defining the rest, the complement of the, you take the entire universe, take the complement of that object, and if you have defined that object, you have defined, if you have defined the complement, you have defined that object. Is this clear? A man is known by the company he keeps. You don't need to know the man, you just look at the company of. So it's like that. So what's happening here is there is a screen with an infinite number of holes. That means the screen is simply not there. So you are imagining that, you're imagining the absence of a screen as a screen with an infinite number of holes. Why? Because if you think of the absence of a screen, you're talking really about the motion freely of a particle from its initial position to its final position. But when you talk about the absence of things there in between, in terms of a screen with an infinite number of holes, you can actually try to understand quantum mechanics by generalizing Young's double slit experiment to a screen with an infinite number of holes. So that's the idea. Okay, next slide, please. Actually, let's before this, can you please show that picture? That picture should make it clear. There's a picture. It's called multiple.
Yes. Yes.
Okay, so here you see this is screen. There's a source S here, and as usual, the student was interested in punching an extra hole in the screen. So now you have three holes: A1, A2, A3. So what's going to happen? Light from the source S comes to these three holes A1, A2, A3. A1, A2, A3 will act like secondary sources, and light comes through them. But then you put another screen here, and that screen In that screen, you make, let us say, 4 holes, B1, B2, B3, B4. So A1 acts like a source for each of these holes, slits, and then A2 similarly is a source for each of these slits. A3 is a secondary source for each of these slits, 3 or 4 slits. Now B1, B2, B3, B4 themselves are like tertiary slits, tertiary sources. So light goes through them and then you observe it on the screen. So what's going to happen now? The light starting from S reached O through multiple paths. It can go through any of these paths. Is that right? And it has to be this way because we are interested in summing up the amplitudes, and we interpret each of these A1, A2, A3, B1, B2, B3, B4 as secondary sources of light. So this is what the student was asking for. Suppose instead of having simply A1 and A2, I have 3 slits, then what's going to happen? Okay, fine, I have these 3 slits. Suppose I put another extra screen and which has a certain number of holes, what's going to happen? And so on and so forth. Well, the answer is simple. In each of these cases, you look at the amplitude of the wave coming out of this B1, B2, B3, B4, you add it and you get O. And what about the amplitude of the wave which comes to B1? It can actually get contribution from A1, A2, A3, and so on and so forth. What about A1? It gets contribution from S, and so on. So you just add all the amplitudes. That's all you need to do in order to find out what the amplitude and therefore the intensity is on the screen on which O is sitting. Okay. The interesting limit that we are interested in is where there are an infinite number of screens and there are an infinite number of holes in each screen, which is a very convoluted way or a fancy way of saying actually there is nothing. There is a source S, there's a, from where a particle is starting, there's a point O where it is headed to, where the observer is sitting. Everything else in between is Maya. Okay. It's absence of the screen. It is having a screen with an infinite number of holes. These are all the same words. Okay, so let's go back to the text now.
Yes.
Yeah. So, so before I formalize that notion, let me pause here and I can take a quick question or two that people might have. The previous slide, please. Yeah, freeze this, and I'll just wait for 30 seconds to find out if people have any question.
So
Please don't hesitate because I told you something rather abstract, and but that is the key to this formalizing the idea that I'm going to talk about now. I simply started. Let me summarize in one sentence, and then maybe you can ask me the question. You start with a source of light or a source which produces atoms or something. You send it through a double slit experiment, you get an interference pattern. You do not have the audacity to check whether it has gone through first slit or second slit. If you do that, the interference pattern is destroyed. But if you let it be, you let it do whatever it wants and you just detect at the final point, you find that it produces an interference pattern. Okay. Now you ask, what happens if I put three holes in this screen? The answer is the same. The interference pattern is still produced. It may be complicated. The way we find out is by simply summing the amplitudes for the 3 holes and then taking the modular square. That will give you the intensity that is observed. Now you ask, what happens if I have an additional screen or an n number of screens and if I have an infinite number of holes through them? A generalization of the superposition principle or simple application of the superposition principle repeatedly tells you all you have to do is to associate an amplitude for each of these non-existent holes on these non-existent screens, and you add all the amplitudes, and that is what gives you the final amplitude of detection at the point O. Let me pause here. I'll take any question. I'll give you 30 seconds to ask me a question.
So from audience side, any questions? Please feel free to ask the questions to the professor.
Yeah.
Audience, you can either unmute your mic, ask the question, or you can mention in the chat box.
Is there a question?
Yeah, from participants, if you have any
Yes, sir.
queries.
Yes, sir. I have one question, sir.
Yeah.
Yeah.
What is your name, sir?
Sivaselvan, sir. Sivaselvan.
Are you from?
Mannargudi. Mannargudi.
Okay, okay.
Sir, is there any easy way to form Michelson interferometer in practical, sir?
Okay, so this is outside the scope of this talk. I think
It
that
is
should be
related to
considered.
interference, sir. So that I am asking that question, sir.
Yeah, sure. But I think
Okay.
we just go on to tangent and lose time. Already we are doing badly with time. So please send me an email that can.
Okay, sir. Okay, sir. Okay, you carry on, sir. Carry on, sir.
Something which is immediately relevant to whatever I have said till now, please ask if you want. Okay, so if there is no question, I can continue. But now, Dr. Vijayaraghavan, you have to tell me, should we take a break or should I
Sir,
continue?
Professor, I think we have to take a break of 10 minutes. I think we have to reassemble around 11:30.
Yeah,
Is it okay, sir?
because because this is the right point to take a break. I don't want to
Yes, sir. Yes,
stop
sir.
later.
I think
Okay,
I will
so
start by
we-
11:30. So
Okay,
you tell me the time, sir. After 15 minutes?
Sure. That I am fine. 11:30 is fine.
Yeah, 11:30. So
Yeah.
I request the participants, you have to reassemble again. We have a 10 minutes break. 11:30 we'll have to assemble here. Thank you. Thank you, Professor.
Thank you.
Hello, is it audible?
Yes.
Can we, sir? Can we start?
Yes, yes.
Yes, this might eliminate all the participants. So,
Yeah, can you share the screen now?
Yeah, I am ready. You can see the screen, please. Yeah. So if you tell me when to start, I will start.
I think
yes,
we can
I think
start,
we can start this so we can start the session.
I can start?
Yes,
yes,
yes.
yes, sir.
Okay, good. So let me briefly recapitulate. What we found was that if there's a particle, it could be a photon or an atom or whatever, it starts at a point S, that's the source, and it ends up at a point O where it is being observed. So there's an initial point and there's a final point. We are asking the question, what is the amplitude? What is the intensity for finding the particle at the point O? Which can be answered if you know what the amplitude for the particle is, which itself can be answered if you know the amplitudes of that the particle takes, the amplitudes for the particle to pass through the various slits that we have put up. Now, if you put up an infinite number of slits on an infinite number of screens, it simply means you have not put up anything in between. But nevertheless, from a Young's experiment point of view, you need to add all these amplitudes. So we need to formalize this idea. So we want to write down one simple equation which explains this. So I'm calling A the amplitude. What is the amplitude? That is the amplitude for going from the point S to the point O. But that amplitude is a sum over all the amplitudes. Each of those amplitudes on which you're summing is actually for the amplitude to go from the source to the observer in time t along a given path. Okay? Why is it? And then for each path, you have a zillion paths like that starting from S to O, and you have to sum over the amplitudes for each of these paths. Why? What is the sacredness? What is the sanctity of this path? This path itself is a path because there are a zillion paths now. There are an infinite number of paths now, simply because there are an infinite number of slits on a non-existent screen. If it's if it's a screen which exists, you can say there are 10 holes on it or 10 billion holes on it. But if there's a screen which does not exist, it means there are an infinite number of holes on it. So there are actually an infinite number of paths from the point S to the point O, and each of these paths can be thought of as a path traversing through one slit which is absent, and therefore we need to associate an amplitude to that. So let's look at the picture for this. So there's a picture which is called, I don't know, the paths or something. Can you see? I don't remember the name of the picture.
All the paths, all paths.
All the paths. Yeah.
Yes.
Yeah, so you see, in the previous slide we showed there are two screens with a certain number of one screen having 3 holes and the screen having 4 holes and so on and so forth. Like that, in principle, there are actually, you can think of multiple screens with a certain number of holes, and the particle can basically traverse through these holes in any which way it wants and start from the point S and reach the point O. Right? So it could take a very simple path, it could take a very curvy, wiggly path, it could actually do all sorts of complicated things before it actually reaches the point O. As I told you, the source from which it comes, that is known to us, that is something we set up. The observation point is something which is now in our control, we can actually make a measurement. Sorry? Can I continue, or is there a question?
No, there's no continue.
Yeah. So the only things that are under our control are the source S and the observation point O. In between, what it does is entirely up to it. So you can imagine this lack of knowledge that we have as basically the presence of an infinite number of screens in between S and O, each one having an infinite number of holes, and the particle can go through any hole and any screen any number of times it wants in any path it wants. So basically, associated with each of them, you need to assign an amplitude, and you have to take that amplitude into consideration. That's what this picture is telling you. Okay, let's go back to the text, please. Yeah. So this A is basically the sum over all the amplitudes. Each of those amplitudes is the amplitude that you assign to go from point S to point O in a time t along a chosen path. And you sum over all these paths. That's what the first equation is telling you. This is the gist of everything that we have learned about. This is what the Young's double slit experiment is suggesting to us, and this is what we are. This is how we are formalizing this idea. Okay, but then at this stage, it's simply an idea. We'd like to know, we have written down an equation, that is fine, but what do we mean by sum over paths? How does one sum over paths? That's a question that naturally arises. Well, the answer for this is fairly simple. We already know from Newton and Leibniz that if there is a path from one point to another point, it can always be approximated by a sequence of small straight line segments, right? So you take a small, you take one step at a time, a small step, and then you take another step, another step, another step, like that. So you can conquer any finite distance along any path by taking small straight line steps one at a time. So that's the idea. Okay. Okay, that is, let's say we are able to implement that idea. Then the question that naturally arises is, what is the amplitude along a path? First we said, what is the sum over paths? We have some idea. And what is the amplitude along the path? Well, the amplitude along the path is something we are saying the particle is starting from the point S and reaching the point O in a time t. So basically, if you think of this as a quantum mechanical system, it is evolving in time. But quantum mechanics tells us that the amplitude to go from one point, from initial point Qi to the point Qf, is basically given by the unitary operator, which is the time evolution operator, e to the minus ht, where this capital H is the Hamiltonian and t is the time that you need to go from the initial point to the final point. Right? This is the unitary operator which gives you time evolution. In quantum mechanics, time evolution is given by the generator for time evolution is the Hamiltonian, and the exponential of the Hamiltonian operator. The Hamiltonian operator is a Hermitian operator, and e to the minus iht, t is simply a parameter, time, real parameter. So e to the minus iht will be a unitary operator. As is well known, transformations, space-time transformations in quantum mechanics are given by unitary operators, and this is the time evolution operator that we're talking about. In writing this, for the sake of convenience, I put h bar equal to 1, the Planck's constant. Okay, and that is simply to avoid this very difficult to make these transparencies and put down long equations on these transparencies on the slides. So we just h bar is a universal dimension full constant, so put it equal to 1, and whenever finally after having done all the calculations, you can always restore it simply by appealing to dimensional analysis. This is just for the sake of convenience. I said h bar equal to 1. Otherwise, this unitary operator would have been e to the minus I times the Hamiltonian times time divided by h bar. That's what gives you the right dimensions. Okay. So let me make this notion more precise, because we are not really talking about a point particle and so on. In quantum mechanics, what we are saying is that let this ket q denote the state of a particle which is at q. So it's a position eigenket. If there's a particle at the position q, then the quantum mechanical state associated with that is denoted by this ket q. And the amplitude that we are interested in is the matrix element between the initial ket qi and the final ket qf, and the matrix element that we are computing is that of the unitary operator e to the minus iht, which gives you time translations. Okay, next slide, please. Next slide, please.
So shall I go next slide?
Next slide, please.
Yeah, one for next.
Yeah. Okay, fine. So maybe you should leave the whole thing here and save us time. Yeah. Okay. So now our goal is to compute this matrix element, which is the matrix element between qf and qi of e to the minus iht. Now, how are we going to do that? Now, in physics, there's a very popular rule which was perfected by the British people when they ruled India. It's called the divide and rule policy. Okay, so whenever you have time evolution capital T, so the system is evolving over a finite interval of time t, then I will replace it, as I told you, by small infinitesimal steps. So we take one small step at a time, a small infinitesimal interval of time, and then you repeat it, and you keep repeating it as many times as you want, as many times as you need, so that you you cover the entire time interval capital T. So what I have done is the following: this e to the minus iht I have written as e to the minus ih delta t, where delta t is an infinitesimal time, times e to the minus ih delta t dot 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 e to the minus ih delta t. I have split the total time t into small infinitesimal n number of infinitesimal time steps delta t, and because the exponential of the sum of terms is the same as the product of the exponential of the individual terms, I write e to the minus iht as e to the minus ih delta t, e to the minus ih delta t, and so on. So there's a bunch of terms which are sandwiched between the initial state qi and the final state qf. This is what I need to compute. Okay. Now, how do I compute this? Already it looks a little complicated. So once again, what we can do is take any two of these exponentials that are there, e to the minus ih delta t, e to the minus ih delta t. Recall that there is a famous resolution of identity, which also goes under the name of completeness of states. And if you take any basis set of states that will form a complete basis, for example, the position basis, then it's complete in the sense that if you take a sum over all the projection operators or integrate over all the projection operators when the spectrum is continuous, like in the case of the position eigenstates of a free particle, that must add up to 1. So integral dq, q outer product of q with itself is equal to 1. So this is simply a statement of the completeness of states in quantum mechanics, and mathematically it is simply the resolution of identity. So what do I mean by kill softly? I'll take this complicated expression that I have in the first line and I'm going to stab it as many times as I want. Stab meaning I'm going to insert this identity 1 between two of these exponentials, not just two of between every pair of exponentials. I'm going to insert one identity. That nobody can question, because anything multiplied by 1 is the same 1. And 1 here is, of course, the identity matrix, not simply number 1. The whole thing is an operator. So I'm just going to introduce the identity operator in between these exponentials. So if I do that, what am I going to get? The left-hand side is, once again, qf e to the minus ist qi, the matrix element of the unitary time evolution operator between the initial and final states. That will be now equal to a product of terms. Initially, on the right-hand side, I had a bunch of exponentials which are sandwiched between qf and qi, but because I'm now introducing these the identity operators in between, this whole thing will actually now become a product of matrix elements. So, for example, between the first two exponentials I've introduced qn minus 1 integral over qn minus 1. Between the last two exponentials, I introduced q1 integral over q1, and so on and so forth. And therefore, this entire expression is now basically a product of matrix elements of the form qf e to the minus ih delta t qn minus 1. The next one will be qn minus 1 e to the minus ih delta t qn minus 2, and so on and so forth, till finally you get q1 e to the minus ih delta t qi. It's simply insertion of the identity operator. What I have accomplished is the following. To start with, I had to calculate the matrix element of a unitary operator with a finite time. Now I'm having to calculate the matrix elements. Now I have shown that that whole thing is equal to the product of matrix elements of another unitary operator, but now the time is an infinitesimal time, right? So what we normally say, the total time t is basically made up of small infinitesimal steps. That statement is reflected at the level of the operators in the following fashion. The matrix element of the unitary operator with finite time is equal to the product of the matrix elements of the same unitary operator but with infinitesimal time slices. That's what I've done. Okay. So now at the end of the day, all I need to do is to know how to calculate each of these products or each of these matrix elements in this product. Namely, I need to calculate how the last line. I need to calculate typically a matrix element of the form qj plus 1 e to the minus I delta t, the Hamiltonian, sandwiched between the e to the minus I delta t, the Hamiltonian, sandwiched between qj plus 1 and qj. Is that clear? That's the last line, I think, is being blocked by this display. Yeah. Okay. Yeah. So basically, each of these terms is of this form qj plus 1 exponential of ih delta t qj. But now, for the sake of simplicity, let me take the Hamiltonian to be the Hamiltonian of a free particle. So it's p hat square. P is the operator, so p hat square divided by 2m. So I substitute that for h. So I have e to the minus I delta t p hat square over 2m, and I have to calculate the matrix element of this operator between the states Qj and Qj plus 1. Why? Because that is the typical element that appears in the previous expression. And if I know how to calculate this for generic J, then I know how to calculate each of these terms, then I simply have to take the product. Okay. But there's a problem. I'm having to calculate the matrix element of an operator which depends on the momentum in the position basis, because Qj and Qj plus 1 give me the coordinate basis like this. Right? So there's a way out of this, and that is simply, once again, kill softly again. You introduce the resolution of identity, but this time you use the momentum eigenstates to do that. So integral dp over 2 pi, the outer product of p with itself is equal to 1. So I insert that one. So the left hand side, Qj plus 1, the matrix element of e to the minus I delta t p square over 2m between Qj plus 1 and Qj turns out to be integral over dp modulo by 2 pi times the product of the matrix element of e to the minus I delta t p square over 2m between Qj plus 1 and p, and then there's another factor here which is the inner product of p with Qj. Now life is simple, because on the right of this e to the minus I delta t p hat square over 2m, you have a momentum eigenstate. So the p hat, so this p is an eigenstate of the momentum operator p hat with an eigenvalue p. So this operator, you can make it act on it and it just becomes a C number. You can bring it out of that matrix element. And what will you be left with? You will be left typically with inner products of the momentum with the coordinate or vice versa. But that is something which is very familiar to us. Can we go to the next slide, please? So recall, now p hat acting on p simply gives you p, which is the eigenvalue p, just a number acting on the same state p, because p is an eigenstate of p hat. And we know that the inner product of p with q is equal to e to the minus I pq. Why do we know this? Because p is a momentum eigenstate, q is a position eigenstate, and the position eigenstate seen in the momentum basis or vice versa is simply given by a plane wave. That's basic quantum mechanics. So you have pq is equal to e to the minus I pq. If you add qp, that will be e to the I pq. So these are basic results. Now it's very simple to compute this Qj plus 1 e to the minus I delta t p hat square over 2m Qj. As I told you, p hat acts on the p vector, p ket to give you simply e to the minus I delta t p square over 2m, and then you are left with this Qj plus 1 p times Qj, p Qj. But that I told you is simply given by this e to the I pq. You substitute everything, and this matrix element for this infinitesimal time simply turns out to be this ugly looking factor minus I 2 pi m divided by delta t, the whole thing under root. Then you have e to the I delta t m by 2, and then you have in the exponent Qj plus 1 minus Qj divided by delta t the whole square. Next line, please. So now, if you want to compute the original matrix element, all you have to do is take terms like this, because the original matrix element has been replaced by a product of matrix elements involving infinitesimal operators, and we know how to compute the infinitesimal operator. That's what we have just done. So you just need to take the product of those infinitesimal operators in order to get the matrix element of the finite operator. That's what I've written in the next line. I have used the fact that you have a bunch of exponentials, you're multiplying them. So the product of exponentials is equal to the exponential of the sum of the exponents. That's what the last line is telling you. And all this is true here because we are just talking about, the exponents that we are talking about are simply C numbers. They are not operators. Even if they were operators, the position operators would commute with themselves, momentum operators would commute with themselves. But you should be careful when you have operators which mix momentum and coordinate, because the canonical commutative relation between the coordinate and momentum is equal to 1. They don't commute. Okay. So this is simply the expression that we get. A complicated looking expression, but that's what we get. Yeah. Next slide, please. Okay. So now what is the goal? Our goal is we need to take back, please. Yeah. So this is we have a complicated looking expression. Everything is written in terms of delta t. But what is delta t? Delta t is an infinitesimal time interval. So at the end of the day, like in calculus, we need to take the limit where delta t goes to 0, and that is when till now we are talking about delta t. So we have a discrete number of time steps. By taking delta t going to 0, we are making each of these infinitesimal time steps go to 0, which means we are going to the continuum limit. Therefore, we recover the case where time flows continuously from an initial instant to a final instant. So that is what is called a continuum limit, and that is accomplished by taking delta t going to 0. So what happens to qj plus 1 minus qj? These are the divided by delta t. That's what appears in that exponent, right? So what happens to this? So this is very simple. Q is a function of time, and qj plus 1 is the q at a later instant of time delta t. The difference between qj plus 1 and qj is if qj is a function of time, qj plus 1 is a function of t plus delta t. That's what it means, because qj plus 1 is the coordinate at the next time step divided by delta t. But this is simply the famous formula that we have in calculus. The derivative of a function of x, f of x. If you want to take the derivative, what you need to do is take f of x plus h minus f of x, the whole thing divided by h, and take the limit h tends to 0. That's what we are doing here. So this whole thing here in the limit delta t goes to 0 is actually the time derivative of q. And because there's a square, this is q dot square. In the exponent, this is what we are having. But in the exponent, we also have a sum over these infinitesimal time steps. So this delta t sum over j equal to 0 to n minus 1. So there are n steps, each of width delta t. So if you add them, basically what you're going to get is total time, and that in the continuum limit is simply depicted as an integral over time from 0 to capital T. So that is the limit of delta t going to 0. In the limit delta t goes to 0, this complicated thing delta t sum over j equal to 0 to n minus 1 simply turns out to be the integral 0 to capital T of delta t. So if you put everything there, you find that the matrix element between the initial state and final state of this time evolution operator e to the iht, which we computed by divide and conquer policy, we broke it up into small infinitesimal pieces. Each of the infinitesimal pieces we could compute by inserting a complete set of states. And once we computed that, we got an exponential, and therefore we had to take the product of some exponentials. We took the product of exponentials, that became the exponent of some complicated sum, but that complicated exponent in the limit delta t goes to 0 reduces to simply e to the minus I 0 to capital T dt times m by 2 times q dot square, and that's what we get in the exponent. But of course, can you please go back? Yeah, no need to go back. I've written it here. There were a bunch of other terms, and those other terms were minus I 2 pi m over delta t. You remember under square root, we had that under square root, but there are n such terms now because we broke the original matrix element into products of n product in n-fold product of matrix elements, infinitesimal matrix elements. So there will be n such terms. So you get a factor minus I 2 pi m over delta t to the power of n by 2. And then of course you had the product of these terms, which is this product j 0 to n minus 1. And then there was an integral over dqj that came from the fact we were inserting a complete set of states everywhere. So all this junk that was there, we dump it because it's an overall thing, and that's what actually defines for you this dqt. Recall, when we tried to formalize this idea, the very first question that came to our mind was, okay, fine, I am going to sum over all these paths, but what does sum over paths mean? How do I do it? Well, sum over paths means the following. If you had a discrete finite denumerable set of paths, you would sum over those paths. But because now we have an infinite number of slits and an infinite number of paths, and these paths can continuously vary from one to the other simply by changing time, they're functions of time. Therefore, you sum over these paths is replaced by an integral over these paths. And if you have replaced it by an integral over paths, you have to mention, instead of saying what is the sum over paths, the question that you have to ask is, what is the measure of this integral? And that is this measure dq. This is the definition of that dq. And this is not something we have put in by hand. This simply came out of the formalism. This came out of basic quantum mechanics. We have not used anything more here except for a complete set of states associated with the position and the momentum. That's all. And the fact that time evolution is given by the unitary time evolution operator, which is generated by the Hamiltonian. These are the basic inputs of quantum mechanics that we have used in order to compute this matrix element between the initial and final state, and which now we are actually able to rewrite in the form of an integral over all paths. Okay. Let me pause here and digest this idea. What we said is we have an initial point and a final point, and there's a system, quantum mechanical system. It could be a photon, it could be an electron, it could be a neutron, it could be any quantum mechanical system which is going from the initial state to the final state. The initial state we are calling Qi, final state we are calling Qf. We are interested in knowing what is the amplitude for this transition. The amplitude for this transition is defined to be the matrix element of the time evolution operator between the initial and final states. And we have derived an expression, integral expression for such a matrix element. That integral expression involves integrating over all possible paths which join the initial point with the final point. But that integration is not simply a sum over all such paths. Each of those paths is weighted by a factor, and that weight factor is this e to the I is integral 0 to t dt of m by 2 q dot square. Now, if you recall, we are talking about, we chose our Hamiltonian to be the free Hamiltonian, and therefore this m by 2 q dot square is simply the Hamiltonian of a free particle. In other words, it's simply the kinetic energy, because for a free particle, the entire Hamiltonian, the entire energy is contained in the kinetic energy. What would have happened if I also had a potential energy? So the Hamiltonian would have been p square over 2m plus some v, where v is a function of q. Now I leave it as an exercise for you to work out. Remember that v is a function of q. So when you are trying to compute a matrix element of the form qf e to the minus iht qi, that is in the last line, then you will have a Hamiltonian which involves both p and v. So you will have to insert a complete set of states, once again momentum eigenstates or position eigenstates. If it's a momentum eigenstate, the p hat can act on it and just be converted into a number. If it is a position eigenstate, the v can act on it. V acts like a c number. The v does not act like a c number. It acts in a more complicated fashion if it acts on a position eigenset. And likewise, the momentum operator p acts in a complicated way if it acts on a position eigenset. The v operator acts in a complicated way if it acts on a momentum eigenset. Therefore, you have to judiciously introduce the right complete set of states in order to compute the matrix elements involving the operator v and the operator p. Okay, so anyway, if you do that, it's a long exercise, but it's a straightforward exercise. It's clumsy, but it's along the same lines. Conceptually, it's along the same lines that I have outlined. If you do that, what you will find is the following. Instead of getting in the weight for this for these paths in the path integral, instead of that being e to the I 0 to t of dt half m by 2 q dot square, it will now be m by 2 q dot square minus v. Now you will recall that m by 2 q dot square minus v is the difference between the kinetic energy of the free particle and its potential energy. It is what is called the Lagrangian. And the time integral of the Lagrangian is what is called the action. So what we have here is this. The final answer is integral over all the paths qt, which start at an initial point and end at a final point, times what is the integrand. So the measure for such an integral is given by this dq, which is some complicated mess. And what is the integrand? The integrand is the weight that you associate to each of these paths, and that is simply e to the I s over h bar, where s is the action of this path. And s is the action, therefore it's integral over time of this Lagrangian. So this, after all the song and dance, this is the amplitude that we have for the particle to go from an initial state qi to a final state qf. Is expressed now as an integral, but that's expected because we said we have an infinite number of holes, and therefore we have to add all those amplitudes. But each of those amplitudes vary continuously. Each of these, because it is a continuum of holes, basically instead of summing over such amplitudes, we have to integrate over such amplitudes, and that is what this expression stands for. So this is the summary. The amplitude for the system to transition from an initial state qi to a final state qf is given by an integral over all paths which join the initial point to the final point, weighted by this exponential e to the I s over h bar, where s is the action of this particle. This is the summary of what is called path integral in quantum mechanics. Why we do path integral quantization, all that is a different story. But this is yet another approach to quantizing a system. As you recall, you can, if you're starting with a classical system, there's a way to quantize it, namely Schrodinger quantization. Or you can use Heisenberg's approach. Both the Schrodinger approach and the Heisenberg approach crucially use the Hamiltonian of a system in order to define what the corresponding quantum theory is. Here is an example where instead of the Hamiltonian, it is the Lagrangian which plays a role. In fact, Feynman was motivated to find an answer for this very question. In classical mechanics, we have a Lagrangian formulation and a Hamiltonian formulation. Is there a formulation of quantum mechanics which uses the Lagrangian instead of a Hamiltonian? That's what motivated Feynman to come up with this formalism. Although it must be mentioned that the same idea had occurred earlier to Dirac and also to Schwinger, who have also independently discovered the path integral. But somehow in history, this is known as the Feynman path integral. It's more famous as the Feynman path integral. Okay, can we go to the next slide, please? Okay, can we go to the previous slide, please? Actually, sorry, I forgot to mention one point. Yeah, no, the previous one. Previous slide. Yeah, right. So here, if you look at the third line here, on the left-hand side, I have an integral over the momentum of some complicated, bizarre object, and I said the answer is given by this. Okay. So what I skipped, what I forgot to mention, was the fact that this integral has been computed, and this integral gives you this answer. Now, this integral looks very clumsy, but let's not panic. Let's stare at it. Forget about the 2 pi. It's just a constant. It'll come out of the integral. So you have integral over dp. So you're trying to do a one-dimensional integral over the momentum. Okay. And what are you integrating? The integrand is, what is the integrand? The integrand is exponential of now minus I delta t. Call it some name, alpha or a or something, some number. Okay, 2m. These are all just some constants. So basically, what you have is some e power, some constant multiplying p square. Right? And then you have another term where you have e to the ip times something else. Now, of course, q is coordinate and so on, but insofar as this integral is concerned, it's simply a spectator because you are integrating over q over p. So everything else is a spectator. T, M, delta T, Q, all these things are spectators. Insofar as the functional dependence on the momentum is concerned, this is simply exponential of something which is at most quadratic in the momentum. So integral dp e power something times p square plus something times p. That's what this is, in the form of this integral is. And it is because of that I have been able to do this integral exact. Such integrals are called Gaussian integrals, and one can actually exactly calculate this integral. So that is the answer that I've given here on the right hand side. So now let me explain quickly how such integrals are done. Can we go to the next slide, please? Next slide. Yeah. So okay. So this is, let me explain quickly. So as I told you, the kind of integrals that we are interested in are some exponential of something which is quadratic in the integration variable. For example, let me call this integral g. So let
Participants are please kindly requested to mute the mic.
Yes, Professor. Okay.
yeah. Am I audible?
Yes, sir. Yes, sir.
Yeah. So let me look at an integral of the form minus infinity to plus infinity dx into the minus x squared by 2. So this is precisely the kind of integral that we were looking at. An integral over x, and the highest power that you have in the exponent is quadratic, e power x squared. Okay. Now, one thing is important. It cannot be plus x squared, then it will blow up. It's unbounded as x goes to infinity. But e power minus x square, if you actually plot this, you will know that this is actually a well-behaved function. It's the so-called the bell curve that you get. It's peaked around x equal to 0, and then it's going to die off exponentially as you go, as x increases. So it is this function that you're trying to integrate. So the trick is to do the following. Instead of integrating directly and finding the answer for g, let me actually compute g square. And what is g square? G square will be minus infinity to plus infinity dx e power minus x squared by 2, and minus infinity to plus infinity dy e to the minus y squared by 2. The product of two such integrals. So that thing I can use plane polar coordinates and convert from x, y, which are Cartesian coordinates, to plane polar coordinates r and theta. If I do that, this thing I will get is exponential of x square plus y square, which is nothing but r square. And theta dependence separates out, and I can calculate the theta integral that will give you actually 2 pi. And then you are left with an integral over r, and that is this 0 to infinity dr r e power minus r square by 2. But this again is easy to do. All you need to do is make a change of variables, call r square equal to r square by 2, you call it w, and then this integral simply becomes integral 0 to infinity of dw e power minus w, which you can compute. Exponential, integral of an exponential will be an exponential. You can compute and put the limits. So if you did all that, what you will find is the following answer. The second line, you go to the second line, minus infinity plus infinity dx e power minus x squared by 2 will turn out to be square root 2 pi. That's understandable because I told you the angular integration separated out here and gives you 2 pi, and g square is like 2 pi, therefore g goes like square root 2 pi. So this is the answer for this integral, minus infinity plus infinity dx e power minus x squared by 2 is square root 2 pi. From here, we can straight away find out what the answer will be if I had in the exponent, instead of minus x squared by 2, suppose I had minus ax squared by 2. That integral is easy to evaluate. All I have to do is again a change of variables, a scaling, x goes to x by square root a. If I do that, this integral, which involves minus ax squared by 2, will be transformed to an integral of the form minus x squared by 2, and the final answer that you will get will be square root of 2 pi over a. But if you recall, we had an integral which not only had a quadratic term in the exponent, but also a linear term. So in fact, if you know how to compute this integral, Gaussian integral g, you also know how to compute a more complicated integral that I've given you in the last line. That is integral 0 to minus infinity to plus infinity dx e power minus ax square by 2 plus j of x. The entire thing is in the exponent. So there's a quadratic term in x, there's a linear term in x. How do I do this? It's very simple. Recall that minus ax square by 2 plus jx, I can write it as minus a by 2 times in brackets x square minus 2jx by a. And then I can do complete squares. So this will be minus a by 2 x minus j by a the whole square. There's a printing mistake here. This 2 must be a power. So x minus j by a the whole square. But then I'll have to add some term in order to make this a perfect square. That is j square by 2a. But that j square by 2a is a constant. Therefore, it comes out of the integral, and I get e power j square by 2a. So the answer is minus infinity to plus infinity dx e power minus ax square by 2 plus jx. If I had, that answer is square root of 2 pi by a, square root of 2 pi by a e power j square by 2a. It is precisely this integral that I used in order to compute that momentum integral, and that is how I found the matrix element of the infinitesimal time evolution operator. And then I took the product of those infinitesimal time evolution operators, and eventually I took the infinitesimal time slice. The limit of that infinitesimal time slice go to 0. That's when all the sums became integrals, and I got the path integral expression that is under consideration. Next slide, please. Yeah, okay. So maybe it has already been a heavy dose of formalism. So let's take one step backwards and then try to understand so that we get our feet firmly grounded where all this is coming from, right? So in order to understand, quantum mechanics is an abstract subject, whereas classical mechanics is something which is very practical, something that we can experience on a day-to-day basis. So our roots are classical, but our formalism is kind of abstract quantum mechanics. So in order to understand that, it's always used to go back to our roots, that is to connect this quantum mechanical formalism to the classical limit. So how does one get the classical physics out of quantum physics? Well, the reason quantum physics exists is because there is a universal dimensionful constant, namely h bar. So if you actually turn off the h bar, if h bar goes to 0, and that's when you get classical mechanics. So classical mechanics is a kind of a limiting case of quantum mechanics, and that limit is obtained when h bar tends to 0. In the similar sense that non-relativistic physics is a limit of relativistic physics. In the limit c, the velocity of light goes to 0, we recover non-relativistic physics from relativistic physics. So in a similar way, in the limit where the Planck's constant goes to 0, you're supposed to recover classical physics from quantum physics. So we'd like to understand how this thing works. So at the end of the day, our path integral looks like this. You have an integral of minus infinity to plus infinity dq, and what you had was e power minus s 1 over h bar times s, where s is the action. Now, actually, sorry about this, but can we go back to the slide which displays the path integral? I just want to add one comment there. That's 2 slides back. Can we go back 2 slides, please? Hello? Can we go back a couple of slides?
1 second, sir, please.
One more slide.
This one, sir.
Yeah, so please pause here. So you see, if you look at the final expression that we had derived, this amplitude for going from the initial state to the final state is simply an integral over all these paths e power minus is over h bar. And this s turned out to be the action, which is an integral, time integral of the Lagrangian. So all that is fine. But recall here, I sneakily brought back the h bar. Okay. You remember when I first wrote down the expression for the time evolution operator, I suppressed the Planck's constant h bar. I set it equal to 1. And I told you at an appropriate time, I'm going to bring it back using dimensional reasons. Okay, and this is where I brought it back. I have e to the is over h bar. And the reason why I know that it has to be of this form is the following. I can ask, see, I remember that I put h bar equal to 1. So now I'm supposed to restore it, and I told you I'm going to use dimensional reasons. So what? So where should I put the h bar? That's a question that I'm not naturally going to ask. We should recall that the action for any system has the dimensions of h bar, the Planck's constant, right? The h bar itself has the dimensions of angular momentum. The action also has dimensions of angular momentum. Therefore, the action and the Planck's constant have the same dimensions, and therefore I have to divide the s by h bar so that the exponent will be dimensionless, and the exponent has to be dimensionless. Otherwise, you cannot write down exponential of some dimensionful object. Doesn't make sense, because if you expand that exponential, different terms will have different dimensions. So the exponential must have an exponent which is dimensionless. That suggests that the h bar should come in the denominator. It should divide the s, because s has the same dimensions as h bar. Okay, so now let's go to the final slide. So now we are interested in taking h bar going to 0 of an integral of this form, right? So you have e to the minus 1 over h bar f of q. This f of q is the s that we are talking about. What we need to do is to find out what happens in the limit h bar goes to 0. So sorry, in this expression there's a typo. This f also should be in the exponent. So e to the minus I h bar times f, that's the exponent, right? So our path integral is of this form, and we'd like to know what happens to this when h bar goes to 0. So the way to understand this is to what is called the saddle point approximation of this integral. What do we mean by that? So you have an expression of the form e power minus 1 over h bar times f. Okay, and you're taking the limit h bar goes to 0. If h bar goes to 0, then 1 over h bar goes to infinity, and you are having e power minus infinity. The whole thing is going to vanish, right? So it's going to die off very fast. So in the limit of h bar, small h bar, this integral will actually be dominated by the minimum of this f of q. Remember, sorry about this. This is a very bad. This f is also in the exponent. This f is also in the exponent. There's some crosstalk. Right. So this f is also in the exponent, and we are interested in finding out what happens to this integral as h bar goes to 0. So as h bar goes to 0, this integral is going to be dominated by the minimum value of f. So how do I find the minimum value of f? Or for that matter, how do I find the minimum of any function? Well, the minimum of any function is defined by setting the first derivative of that function to 0. So if I take this f of q, and if I make a Taylor expansion around the point q equal to a, then I get f of a, plus I'll get a first derivative term. But because I'm saying I'm looking for the minimum of f of q, I set that first derivative term equal to 0. Then I'll get half of f double prime a, which is some constant, because it is the second derivative of f evaluated at the point q equal to a, times q minus a the whole square, plus higher order terms. That's what the Taylor expansion of this f will tell me. Now I can substitute this f of q in that previous expression, in that first line, in the integral I. If I do that, f of a is a constant, so it comes out of the integral. So I'll get e power minus 1 over h bar f of a. Then the remaining thing is exponential of half f double prime a, which is some constant, times q minus a the whole square. So it's basically a Gaussian integral. And I use my famous technique for solving Gaussian integrals, and that will give me square root of 2 pi. You remember? But then there are these additional constant factors. So you get 2 pi h bar over f double prime a under root. That's what the Gaussian integral will give me. And then there are terms of the order square root h, e power minus square root h. They are kind of less dominant terms. You can ignore them. So you see, in the limit h bar goes to 0, this path integral that we are talking about simply reduces to an integral of the, to this form. I is equal to e power minus I h bar f of a, where this f of a is got by extremizing f of q, but f of q, you remember, is simply the action. So the extremum of the action is the one that contributes to the limit h bar goes to 0. But you know that the extremum of the action is actually what gives you the equations of motion in classical mechanics. You get the Euler-Lagrange equations of motion in classical mechanics by extremizing the action. Therefore, this f of a is basically the action, the classical action. Therefore, in quantum, in the limit h bar goes to 0, this path integral reduces to classical mechanics as expected. But if h bar is not 0, then there are systematic corrections to classical mechanics. That is what this path integral is capturing for us. That's why this is yet another way of quantizing a classical system, other than the Schrodinger and the Heisenberg pictures. The path integral way is a way of quantizing classical systems. What we have shown is that we recover classical mechanics in the limit h bar goes to 0. In the same sense, the Schrodinger equation in the limit h bar goes to 0, you recall, gives you the Hamilton-Jacobi equation. And in the Heisenberg picture, in the limit h bar goes to 0, all the commutators essentially, well, that's actually a map reduced to the Heisenberg equation, for example, reduces to the corresponding Liouville equation and things like that. Phase-space classical phase-space mechanics. That's what happens in the limit h bar goes to 0 for Heisenberg in the Heisenberg picture. In the limit h bar goes to 0, the Schrodinger picture reduces to the Hamilton-Jacobi equation, which is again a classical equation. And in the limit h bar goes to 0, the path integral will give you back the Euler-Lagrange equations, which is yet another way of doing classical mechanics. So that completes the story about the birth of path integrals as a way for studying quantum mechanical systems. Of course, it's a very, very vast subject and a very important subject. I've barely given you glimpses. The tip of the iceberg is what we have seen. There's a lot more to be learned about it. I just hope I gave you a small flavor of this. If anybody is interested, they can read a lot more. There are many, many very good books which discuss this, including the famous one by Feynman himself, Feynman and Hibbs. Okay, I think I will stop here. Thank you for your attention. Sorry for all the technical glitches.
Thank you, sir. Now the session is open for discussion and participants. Please mute your mic for a small discussion. So there is a question in the chat box. The question is, when we slice time, suppose for Hamiltonians and T plus dt, then can I do the same predicted problem? Professor, Mr. Narashima is A. Can you just unmute your mic and just ask the question directly to the professor? Any other questions, basic comment questions from audience side and other participants?
So I guess the formalism is a little bit heavy, and unfortunately there is no escape from that. And these kind of things, the best way to learn them or to become confident and about these things is to actually work out all the details. I've given you the summary of how to approach this subject, and it will take some time, but maybe it will be worth the time if you spend working through all the calculations. I think you will enjoy it. But if there are any questions, I'll be happy to answer.
Yeah, participants,
now
do you have any?
If you have any questions, I'll be happy to answer. Thank you, Ashok Kapoor.
Yeah, participants, do you have any queries? I think so. We have to study in detail because this is just a brief introduction about the integral part. So when we go through in detail, definitely we may have to proceed further. Thank you, Professor. Thank you for your excellent presentation today.
Thank you. The pleasure is all mine.
Yes, sir.
Have a good.
Yes, sir.
Yeah, I'll be happy to answer if anybody has any questions. If not now, later you can send me email. I'll be happy to answer. Yeah.
Yes, sir. Yes, sir. Sure.
Hello.
Yes.
Through email.
Professor, thanks for your wonderful lecture. I am Dr. Vijay Sundaram from Nagapattinam.
Yes. Thank you.
As you told, visualizing the concept in quantum mechanics actually a bit difficult because of we are not actually experiencing those phenomena in day-to-day activities. Maybe we are not able to observe it as we do in classical mechanics. That is also one of the difficulty for understanding the subject. As you told that, I agree. But teaching quantum mechanics, I'm very new. The students, for example, if you take Gaussian integral or any mathematical concept, when we are doing it for arriving at the solution, the students ask, why are we doing it? But I fail to answer most of the times. I am not able to get it. Is there any kind of suggestion or the books which relates the physical significance? This is what we are doing in every, not in every step, or at least at the end of your few steps. This is the physical significance of doing it. Is there any kind of resources or books or any kind of forums? If you know, kindly let us know, sir, which will be very beneficial for the student. Thank you very much, sir, for your wonderful lecture. Please answer, sir.
You're welcome. So there are 2 points I'd like to make here. One is, even the most famous scientists and the greatest intellectuals have had problems with quantum mechanics and understanding it and visualizing it and so on, right? In fact, the common joke goes that even Bohr and other people, the common joke is that if you say you understand quantum mechanics, actually that means something is wrong. So, but obviously this is not an answer that you can give to students. So the point is the proof of the pudding is in the eating. If you say these are the rules by which I'm going to play a game, okay, and you stick to those rules, and if something goes wrong, then you're willing to modify that those set of rules, and that is how physics proceeds. That is how any science proceeds. So in order to understand things at a microscopic level, quantum mechanics was invented. It looks like a rather ad hoc set of rules, but the fantastic thing is that these rules explain almost every experiment that you can perform at the microscopic level, at atomic and molecular scales, to a great deal of accuracy. So, and there is no other substitute, no other theory that we know of which is so successful in the history of man's intellectual quest.
Yeah, I will be very happy to. Actually, I have not started a forum. If there is enough interest, we can start a forum on zero space.
Yeah.
Maybe sure. You can send that. Maybe you can send that link to these organizers and then circulate it.
Yeah, I have already written to the organizers that if there is enough interest, I will start a forum on zero space.
Sure, sir. Sure.
I have already written that.
Yeah. Sure.
Thank you, Professor, your wonderful effort and time and answering this question also. Thank you very much.
You're welcome.
Yeah, thank you, sir. Thank you so much, Professor Sridhar, sir.
Professor Sridhar, it was very nicely planned. I am very happy to hear about it because it's a very difficult area to present in 2 lectures. Thank you. Thanks a lot.
Yeah. Thank you. Coming from you, it means a lot. Yeah, thank you. Bye.
Thank you, sir. Thank you, sir. Then the afternoon session, dear participants, the afternoon we have a valedictory around 2 o'clock. So kindly reassemble exactly at 2 p.m. Thank you, sir. Thank you, Professor. Thank you, Ashok Kapoor, sir.
Thank you. Yeah, bye.
Bye.
Thank you, Professor. Thanks to the organizer also.
Yeah. Thank you, sir. Thank you, Vijay Sundram, sir. So where you are, sir? Which college?
EGS Pillai, Nagapattinam, sir.
Okay. It's a government arts college?
Private autonomous college.
Okay. So you are taking the pure BSc MSc physics, no?
Yes, MSc.
Okay.
Physics.
I think it may be essential, no, for you. We have to
yes, sir.
quantum mechanics. Yeah.
Yes, classical
so I think
and
we already requested Professor Ashok Kapoor, sir. I think sir send me the list of the references books, sir. So that.
Okay, sir. Okay, thank you very much. Am I talking to Amiruddin or Vijay Raghavan, sir?
Vijay Raghavan, sir.
Okay, sir. Thank you. Nice of you, sir.
Thank you, sir.
Thank you very much, sir.
Thank you, sir. Thank you. We'll reassemble again. 2 Amit, sir, it is 2 p.m., sir.
Oh, okay, 2 p.m. Yes.
Yeah. Thank you, sir. Yeah, we'll wind up the session now.
Yes, sir. We'll wind up the session.
Yes.